Welcome to the 6th lecture. Now, this week we are going to see impedance matching at microwave frequency. In the last module, that is the last week, we have seen the importance of impedance, how to measure impedance at microwave frequencies. Particularly, we have seen the use of a very elegant tool, Smith chart, and how to use that Smith chart to measure impedance. Now, today we will see that between various parts of a network, if there is an impedance mismatch, then lot of power gets wasted, and in microwave frequency power is at premium, particularly when we are trying to send power from one place to another place. We should always see that what are the places where that power is getting lost. So, we will try to minimize that loss, and for that we need to do impedance matching to prevent that power loss. Now, this concept we will see in this today's 6th lecture in detail. So, today's topic is need of impedance matching at microwave frequency. Now, this is the general thing, that suppose I have a source at the left hand side, you are seeing, and that source is delivering power to the load. Now, obviously, source cannot connect to a load. Suppose a base station of a cellular telephony station, that mobile phone base station, he is trying to send power to various mobile sets that you are having. In that case, how that power, the source of that or the transmitter, that sends the power to a waveguide, and that finally connects to an antenna. So, that antenna behaves as a load to that transmission line. So, in the slide you can see that the source, it is delivering power to the load. Let us consider in your mental frame that that load is that antenna. So, through that there is a transmission line going. Let us see that let us consider that transmission line is having a characteristic impedance of Z naught. The source is having a source impedance, all sources have some impedance, there is no source without any impedance. So, let us call that ZS, and the load, that is having the load impedance ZL. Now, ZS consists of two parts, one is the real part, that is the RS, and another is the reactive part, that is the XS. So, we can always write that ZS is equal to RS plus JXS. Similarly, in the load side we have RL plus JXL, and across the resistance RS there will be a voltage drop, we are calling that VRS. Across that resistance or in that resistance there is a power drop, a power dissipated, that we are calling PRS. The voltage source is delivering a power PS, out of that PRS is getting dissipated in the RS. Voltage source is having an open circuited voltage of Vs, it is an AC source obviously, because you cannot transmit any DC source. And let us consider that similar thing is happening, that when the power is reaching the load, the across the resistive part of that load impedance, that means across RL, we have a voltage drop which is VRL, a power that is getting dissipated into that real part, that is PRL, and in general it is very difficult to have this ZS and ZL equal. So, that generally these ZS, ZL, Z naught, because they are part of different designs, a source designer or a transmitter designer fixes up some ZS to deliver maximum power outside, he tries to make his ZS as low as possible. Similarly, a load, he tries to get that whole part. So, his main objective is to make the RL maximum. Now, Z naught, the characteristic impedance of the line, it may be a waveguide, it may be a coaxial line thing. That characteristic impedance depends on the material and also the various geometrical shapes that various conductors they are taking. So, based on that there are various characteristic impedance. So, there is always a difference of impedance levels between these ZS, ZL and Z naught. That is why let us see what happens. So, try to consider that the power from the source is getting delivered to load. Here I want to clarify one point, that when we say power delivered from source to load, basically we mean power delivered from source to real part of load impedance. That means, basically the power that we deliver to the RL of the load. So, please remember this, because power, the power that we can deliver to XL, the reactive part of the load, that is not useful power, actually that is a reactive power. So, no practical work or much practical work cannot be done with that. That is why when we say power delivered from source to load, we mean power delivered from source to real part of load impedance. That is why we have highlighted that real part. So, this is just a clarification. So, you see that due to those various impedance level, when the power is getting flowed to the load, now from a characteristic impedance of Z naught in the line, it is seeing a load impedance of ZL. So, whenever there is a, we have seen that the wave sees two different impedances, impedance discontinuity, there is a reflection. That reflection we are calling gamma L in terms of power. This is power reflection coefficient gamma L. Similarly, if any power is reflected from the load, it is going to the source side to that same transmission line, and again after reaching the source, it sees that there is a mismatch, because source is having ZS, but the power transportation mechanism, the transmission line is having the characteristic impedance as Z naught. So, again there will be a reflection that we are calling gamma S, the power reflection coefficient at the source. Now, actually what happens, power is continuously bounces to and fro from load to source. So, let us try to see that, suppose the source and load, they are separated by a distance, and the travel time of the wave through that distance, let us call Td. So, this the wave is sent from the source to the load. So, after Td time it goes to load, then as there is a mismatch at the load, some part of the power gets reflected, some part of the power stays at the load. Now, that reflected power again comes back to the source, that will again see a mismatch, because there is a gamma S, a mismatch at the source. So, again some power that will be reflected and go back to the load, again that will face another reflection at the load, that will come back, etc. So, there is an infinite such waves going back and forth. So, at any instant, if I see that what is the total power that is coming at the load, it is consisting of infinite number of previous reflection. The most recent reflection that happened only, suppose if I look at this, that this is the load, this is load and this is source, then you see that suppose now I am here. So, one wave has come just TD time before. So, this source has delivered and it has come here, but this time also another one is coming 3 TD time before there was another wave. So, that came to the load, that came here and again coming back here. Another 2 TD time before there was another wave that was emitted from source that suffered 2 such reflection and came back here. So, all these at a time, all these previous ones separated each by 2 TD, they are coming here. So, if you look at the slide, you will understand that one wave which just TD away, the wave which was emitted by the source 3 TD away from this time, then 5 TD away, 7 TD away, all are coming at the time. So, at any time if I want to find out what is the total power reaching the load, that will be summation of all these infinite previously reflected waves. So, that is why we write that when power arrives at load, basically all these things happen. That let us say source delivers a continuous sinusoidal voltage wave, we call it Vs. The amplitude part is of the voltage source is VSO, and obviously with time we have a time harmonic variation. Any sinusoidal source with a phasor representation we can write as a e to the power j omega t. Now, power is delivered by source at t is equal to 0. Let us consider t is equal to 0 is the time when it has been, we are counting our time presently. So, power will reach the load at t is equal to T d after T d time. Some power stays at load, rates gets reflected. Also, the power delivered by source at all previous time instants given by t is equal to minus n 2 T d away. So, minus 2 T d, minus 4 T d, minus 5 T d, all those ones having several reflections, they are also arriving at the load at that time t is equal to T d. So, a journey of a power wave for a time t, whether both source to load or load to source, is mathematically a phase change by e to the power j 2 omega t. This 2 you please note, because it is a power wave. So, in a voltage wave or current wave it is e to the power j omega t, but in a power wave this is e to the power j 2 omega t. So, a bounce back from load changes the amplitude of the wave by gamma L, as we have seen, and that gamma L power reflection coefficient is related in a square fashion with the voltage reflection coefficient. Same thing for source power reflection coefficient. So, two reflections and source and load changes phase by 360 degree. So, no phase change. With all these things we can now see that voltage load reflection coefficient, this is well known, in last week's lectures also we have used this, that the load reflection coefficient will be the load impedance minus the characteristic impedance of the line by, again those same mistake, ZL plus Z naught it will be, sorry, please see in here, last time also I did not correct it, gamma L is equal to ZL minus Z naught by ZL plus Z naught, and gamma S is equal to ZS minus Z naught by ZS plus Z naught. This plus in the denominator is wrongly given here, and fractional power available for delivery at source line junction. That means, when I have source, so the source side, you see there was source, there was the ZS part, and then when you are giving this to ZL, so this is a voltage divider. So, the fraction of that is delivered to load, and obviously delivered to load means delivered to the real part of load, that is why RL by ZS plus ZL whole square, okay, the magnitude part. Now, each wave delivers some power to the load, cannot deliver its full power. At any instant, power delivered to the load will be equal to mainly, actually it is infinite number of those waves they are summed, but we are separating that just recently emitted wave and all other multiply reflected waves. So, that is why we are making it as sum of two parts. One part is the first part, power delivered by the wave emitted by source at TD time back, just one journey time back, plus power delivered by infinite number of waves emitted by source at NTD time back. Only the difference between these two groups is the first one is the first reflection that is coming, whereas for others there are multiple such reflections have already taken place. So, we can say that with this we can say power delivered to load will be changing with time, because it is a time function that waves are coming and going. So, it will be changing with time. So, we can write an expression for that power delivered by the latest wave emitted by source, that means which was emitted T is equal to TD back at T is equal to 0, that we can write this expression. You can all know that this is the expression of power and for a wave. Similarly, power delivered by the other at T is equal to minus 2D is the second expression. You will easily understand that at load it is first taking one gamma L fractional power, then again at source it is taking one gamma S fractional power. So, that is why multiplication of that, and we have written the general expression at the third expression, that the wave which was emitted minus 20D back from our reference time. So, that when it is reaching the load TD time after, the expression is like this. So, because it has suffered small n number of reflections. So, we can write the expression like this. So, now we can sum the power intensity will be sum of all these, and that we can write as an infinite geometric series. So, we see that this thing is a thing expressed with time. So, with time there will be various values of this power, that is why we say power varies during time with time. So, the time when power is varies, that we call transient state, but as time progresses you see that the whole thing is getting multiplied by gamma s gamma l to the power n. Now, both gamma s and gamma l they are fractions, that means less than 1. So, as we go on increasing the value of the small n, the amount of power that is reaching, that is becoming smaller and smaller. So, we say variation becomes smaller and smaller with time. Finally, a state is reached, after that practically there is no variation. Obviously, there is a variation, but that is so small. So, that time we call steady state is reached, and generally this transient time is quite small. So, after a short time, that depends on the time constant of the whole network, the whole thing goes to steady state and we have a power which is more or less for all practical cases constant. Now, let us see at steady state what is the power lost in mismatch. That is shown like this. You can easily calculate, because if you sum this infinite series for infinite terms, you know that a geometric series, the series may be infinite, members may be infinite, but their sum is finite, and that sum if we put, then we get the power that is delivered to the real part of the load at steady state. That is a finite thing, that is not infinite, and from that we can find out that if there was no mismatch in the whole thing, that means if there was no load reflection, then what was the power, and with load reflection what was the power, their difference is the power that is lost in this mismatch process. Due to mismatch how much power is lost, that we have found, and then you can find the relative power loss. So, that expression finally comes to this, that 1 minus gamma s into gamma L by 1 minus gamma s gamma L. So, this is much less for passive loads, because for passive loads all these reflection coefficients they are less than 1. We have seen while describing Smith chart that if this reflection coefficient becomes greater than 1, that means we have active some devices present, oscillations present, etc. But in case of these loads, if we assume passive loads, then this value is much less than 1. Now, here is a table, from that actually we have generated this table, that we have taken various values of gamma L and gamma S and found out that how much is the relative power loss in percentage. So, you see there are various things, but see the extreme bottom column or the last column of this table. It says that if gamma S is 50% means 0.5 and gamma L is 0.5, then relative power loss is 33%. That means 1/3 of the power is lost in this mismatch process. So, if I am trying to send 3 watts of power, 1 watt power will be lost due to this mismatch. So, let us see that what are the take for the from that table, that if there is no load reflection, then no additional power loss at load. So, power is not lost at load. So, that is a good, that means if we can achieve that gamma L is equal to 0, no load reflection, then no power is lost in this mismatch process. But if we have a given load mismatch, that means given load reflection coefficient, then additional power loss, that means this loss is reduced by increasing source mismatch. Obviously, physically it is correct, because if the source is having mismatch, so again some of that power will come back to the load. So, that can be also seen from the table, previous table, that you see we have kept gamma L's constant, and with more increase in the gamma S, you see the power loss actually is coming down. Take any such case where gamma L is fixed, but with change of increase of gamma S, the power loss that is coming down. So, that is obvious that with increase of source mismatch, we are getting again some of that power is coming back to the load. On the other hand, for a given source mismatch, that means given gamma S, this power loss is increased if we increase the mismatch, because more mismatch in the load means more power is coming to the source. So, that is the deterioration of the power loss. Now, see the worst case thing, 50% power lost when gamma L is equal to 0.5. When if we have gamma L 0.5, then half of the power is lost. In now gamma L 0.5 means VSWR is 3. Similarly, gamma L 0.1, 10% power is reflected. You see, this is gamma L is the voltage reflection coefficient. So, our power reflection coefficient is different, that will be 0.25. We can see that thing, that 0.25. So, here you see gamma L 0.5. So, you see for VSWR 1.23 we have 10% power lost, and in worst case when we are keeping VSWR to be 1.11, 5% power is lost. So, load VSWR is generally kept, that is why it is our drive to keep the VSWR of the load within 1.25%. Also, apart from this loss, there is a distortion associated, because as you see that at any time total power is power what is coming due to the last emitted source plus previous sources. Now, sources, they generally, any oscillator, it has some free running. So, after some time it changes its frequency. That means, the waves which were generated earlier, maybe their frequency was different from what we have. So, when finally we are getting the signal, that time we are getting a distortion in, may get a distortion in the signal, because so many waves which were emitted at different times, they are getting summed. So, some of them may having different frequencies than others, though all of them are emitted from the same source, but sources also, any oscillator is not a stable one, for that you need a costly oscillator. So, otherwise they generally drift a bit, and so frequency changes. So, here we have tried to find out, you see all the mathematical details are explained in the thing. So, what is that distortion we are getting, and remember that distortion in power, it is meaningless, distortion always happens in the voltage. So, ultimately we have found that what is the distortion, power remained on first reflection divided by power remained due to sum of past reflection, and that expression we have given. Now, again we have made a table like that, you can see the table and see that for again gamma L is equal to 0, no additional distortion. So, again additional distortion is more sensitive to load mismatch, the same thing. Now, see the worst case values, that for load VSWR of 3, additional distortion may be 70%. On the other hand, if VSWR is 1.1, additional distortion is 30%. So, you see there is always a high chance of distortion if you have good amount of mismatch between the load and the transmission line. Now, let us do the try to find out under what condition this power can be maximized. So, we see that the power that is delivered to the load or real part of load VRL, that is actually Vs by Zs plus Zl into RL. So, from that we have found the power expression, and obviously if I write the power expression, it comes like that, all of this you know. Then maximum transport will occur when the PRL is maximum, that means when the denominator is minimum. Now, denominator you see sum of two square quantities. So, minimum of any square quantity is 0. So, each of them can be 0, but RS, RL, they are the resistive part. Now, they are fixed, they cannot be changed. So, resistors terms cannot be 0 generally, because it is very difficult to make a circuit without any resistor. Both the source and load, they will have some resistances, but reactive terms, they are frequency dependent. So, we can make that XS plus XL, their sum we can make 0. So, this we can enforce, second term can be forced to 0, that means we can force XS is equal to minus XL, source reactance is equal to negative of load, that will make it minimum, and that time if we under that criteria PRL will be this, then we can see that okay, whether this is the maximum or minimum. For that we can differentiate that with respect to RL, and that gives the condition that RS, that means the source resistance should be equal to RL. So, source resistance is equal to RL, source reactance is negative of RL. So, that means the source impedance, that is complex conjugate of load impedance, this you know is called conjugate matching of source and load. So, if conjugate matching occurs, load power at conjugate match. So, under conjugate match we know what is the voltage developed at the load, that you can work out, because that time no reactive part in the circuit, total reactance is 0. So, voltage, but two equal resistances RS and RL equal. So, half of the source voltage is across RS, half of the source voltage is across RL. So, power we can calculate, that will be the Vs square by 4 RL. So, power delivered to load is maximum, power delivered to load equals power remaining in source. That means, in the across the source resistance, what is the power? The same power you can deliver to the load, not more than that. So, now this is one beauty, this is an byproduct of this thing, that under conjugate matching, since power delivered to load is equal to power remained in source. So, source is giving half power. Now, even if suppose that case I was saying cellular telephony, it is radiating. So, load is not accessible to you, but you can always make a measurement at your source, that across the source resistance, if you find that half of the power is there, that means you know that you have got a conjugate match and load is getting half of that power. So, this is the basis of power measurement. So, at the transmitter itself you can find out how much power the load is taking. Basically, this is power measurement. One of the technique is this, that you find out at which voltage, or you can also find out what is the load. You find out when you are getting half of the power, because you know the source power. So, let us say source power is 1 watt. The moment you see that across RS you are getting half of that power, that means half watt, you know that you have got a match. So, the source is equal to that time conjugate match. Now, since the total reactance of the whole network under conjugate match is 0, so we can say that there is no phase shift between the source voltage and load voltage. So, this is called in phase voltage transformation. So, what is the implication of conjugate matching? One, we have seen that it is maximum power transportation from source to load, transportation of voltage without phase shift. Also, under that case, the gamma L, load reflection coefficient, is 0, gamma S is 0. So, no distortion will be there, no power loss will be there. So, under conjugate match we can get lot of things. So, that is why the conjugate match is a very desired thing at microwave frequency, because lot of difficulties, that power loss, distortion, in phase transformation, etc., can be avoided if we can do conjugate matching. So, this lecture tried to tell you that why conjugate matching or impedance matching is necessary in case of microwave networks, and the ideal impedance matching is called conjugate matching, where the load and source, they are complex conjugate to each other, load and source impedance. Now, in the next lectures we will see that how to design networks which achieves this conjugate matching. Thank you.